on screen right now. Sorry, folks. I'll have to wait for the Windows update. Hey, how's it going? Good. Surprise Windows update right now. So Zoom wasn't working, so I restarted the computer, and then the Windows update came up. We may be delayed a couple minutes. I'm sure you guys won't mind. I'm sure you guys won't mind a little delay because there's a Windows update going on right now. I know, right? Unfortunately not.
I'm like ready to write
I know, it's like registration doesn't last that long.
Oh.
Have you seen this congeniality?
Oh, it is. Yeah. There's no dorms here.
No.
Wow. It's pretty much a shit place.
Dude, name George. Sent you this last night to watch. Right here. Dude, he was so good. Notice how cute. He talks about how the I didn't know like
Was anyone even there? Dude, you guys can live easier. Let's
Hello, can you guys hear me on Zoom?
Yes.
Can you guys hear me on Zoom? You can hear me on the Zoom? Okay. Okay, good. Okay.
Can you hear me double for Zoom? Oh, yes, you can.
Oh. Yeah, turn off that. Okay, so sorry about the delay, everyone. There's technical difficulties. I think Zoom is not working on the computer screen on the computer here. We'll figure that after. So sorry for the delay. How's everyone doing today? Good. Okay. All right. So today we are going to be finishing up 2D conduction. So I have a little bit to go on that, and then we're going to be moving on to transient conduction from there. So right now, I'm hoping the audio sounds okay because I'm going through my iPad audio right now. So I'll just hover over my iPad and just talk directly into that. But then hopefully everyone in the class can hear me okay too. But okay, so we're a little bit late today, but any questions I can answer before we get started? Okay, all right, so let's go ahead and get rolling. Okay, so last time we were here, we were talking about multi-dimensional systems. Okay. All right. So most of the problems that we've been doing up until this point have been one-dimensional heat transfer. I mean, heat only goes in one direction, right? But in reality, you know, we live in a three-dimensional world. Heat can go in any direction, right? And so if you really wanted to solve a multi-dimensional system, you would have to solve the heat equation in multiple dimensions, right? And so, you know, I won't show you the 3D version, but I'll show you the 2D version at least. The point is there. Okay. So this is the 2D heat equation. So you can see here we have partial derivatives. So we have one term that has a partial derivative with respect to x, another term with a partial derivative with respect to y. Okay. And so that means our solution is going to depend on both x and y. Okay. And so in this case, it's t of x and y. Okay. So if we truly wanted to solve these equations in two dimensions, we would solve this equation. Okay. But of course, you know, we don't have the ability mathematically to solve a partial differential equation. So the best that we can do in multi-dimensional situations is to look at very specific scenarios. Okay. And so we spent a good amount of time talking about one very important application, which are fins, right? So fins are a very common kind of design choice or design kind of structure for a thermal engineering system, specifically in cases where you have to offload a lot of heat. So we talked about solving the fin equation. We talked about evaluating the performance of a fin. We spent a good amount of time. So that's a good place to start. But there's a bit more that we can do. Okay. And so today, what we're going to start with is, how we can solve for 2D heat conduction in very specific geometries. And I'll put it in quotes because what constitutes a specific geometry will kind of depend on what's given to us. Okay. So this part of 2D heat conduction is not going to take very long. I expect this probably only going to spend about 30 minutes on this. But if your situation kind of falls into one of these specific situations, then you can use this method, which is actually quite simple. Okay. All right, but the main thing I want you to get out of this is that 2D heat conduction, 3D heat conduction, normally very difficult to solve. If you did want to solve these in kind of a general sense, you have to probably use some kind of code to solve the heat equation. So the best that we can do is kind of these very kind of specific kind of situations. Okay. Any questions on this? This is just kind of a recap of last time. Okay. So let's dive deeper into this and kind of go into what I mean by specific geometries. And so the method that we're going to be going over is something called shape factors. Okay. So what is a shape factor? So a shape factor is basically a coefficient which basically describes how heat moves in a very specific kind of geometry. Okay. Which is a very generic definition, and in fact, you could probably apply this definition to a lot of what we've discussed so far. But I think the best way to describe it is with kind of an example. Okay. Okay. So with this example, let's say that we have a pipe that's buried underneath the ground. Okay. And so let's say that we have this is kind of the topsoil. Right. So we have a pipe that's right here. So out here, let's say we have like a dirt or earth or soil or something. Okay. Right. So let's say that this pipe carries some kind of hot fluid. So let's say that it's a hot water pipe that's buried under the ground. Okay. So what's going to happen? Basically, if we take the temperature of the pipe, so I'll call that TP. Okay. And let's say that the temperature of the earth around it, we'll call it TE. Okay. So because of the fundamental law of heat transfer, if TP is greater than TE, right? So the pipe temperature is warmer than the earth, then we know what's going to happen. We know that heat is going to escape from the pipe, okay, and go into the surrounding earth. Okay. But the question, of course, is how much heat is going to escape, right? And, you know, if you look at this situation, you might think, all right, this looks like kind of a cylindrical system. So we can use our cylindrical heat transfer, right? It's not quite like that because, you know, we kind of have a non-symmetric situation where if we look at kind of the top half of this pipe, right? So everything kind of above the midpoint here, right? There's kind of only a shallow amount of earth, you know, covering the pipe on that side. Okay. Whereas if you kind of look below this midline, there's actually a lot of earth down, right? So kind of the assumption here is the earth kind of goes all the way down. Question, yes? No, 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 it does not at all. It does affect the fluid. So if you have some kind of convection, it does affect the fluid flow because fluid has mass, but heat transfer itself is just energy. So yeah. Mm-hmm. So we have kind of an unsymmetric situation, or a non-symmetric situation. So the fact that, you know, there's less earth above the pipe and more earth below it is going to affect the amount of heat transfer. So, you know, I kind of didn't draw these arrows too effectively here because I kind of drew them all the same, but there is actually going to be a difference in terms of how much heat escapes off the top and how much heat escapes down the bottom. Okay. So what we have here is kind of a true, you know, two-dimensional situation. So if we really wanted to solve the amount of heat that's being lost here, we would solve the two-dimensional heat equation in this entire system, which, you know, we've already kind of discussed is not really that practical, right? Okay, so what can we do here? So turns out this situation where, you know, you have kind of a cylindrical object buried underneath kind of a uniform material is actually quite common. Okay. It's even common above ground too. So if you think about, you know, if you have a pipe that's in air, you know, below that pipe, you're probably going to hit the earth much sooner than you do hit, you know, anything above it too, right? And so because of this, you know, what scientists have done or what engineers have done is that they've taken a bunch of data from these kinds of situations and come up with a way to kind of very easily compute the heat transfer from it. Okay. So this is something that's quite common in science and engineering. You know, probably you've come up with this, you know, probably you've seen this to some degree in the past as well, where, you know, if a certain situation happens enough, you know, there's a lot of data that's collected on it. And then based on that data, we're able to come up with some kind of formula or some kind of equation or some kind of trend, okay? So for this specific situation, which is a, you know, a pipe underneath the earth, okay? The heat transfer from this is computed as the following. So we have Q is equal to, let's see, we have delta T, so we have TP minus TE, okay? So that's the temperature difference between the pipe and the earth, okay? Multiplied by K, okay? Where this K right here is the thermal conductivity of the surrounding earth, of the dirt, okay? multiplied by this factor right here. So we have 2 pi L divided by hyperbolic cosine inverse of 2z divided by d. Okay. Okay, so I'll let you guys write that down. And I'll find the terms there. But there's a few variables that we haven't seen just yet. Okay, so let's define the variables here. So L here is the length of the pipe. In this case, it's the length going into the page. Okay. Z here is the depth of the pipe in which it's buried underneath the earth. Okay, and D is the diameter. Questions? Yes. Yeah, it's from the center of the pipe to the surface of it. So I'll label all these things on the figure. Okay. So if we label all these things, well, the length we can't see because the length is going into the page. But this depth right here is Z. The diameter, of course, right here is D. Okay. And the length is what kind of goes into the page. Okay. Question? Yes. Yes. It can vary. So if the earth is some kind of composite material, so it's made of different constituents, it could vary, especially kind of, you know, spot to spot if there's rocks or things like that. So this would be kind of like the average thermal conductivity of that. Yeah. Questions? Yes, yes. Yeah, sorry. I kind of scrolled down very quickly. Yeah. Okay. So this is good. So for this situation where we have a pipe buried underneath the earth, we have a formula for this because this is something that occurs a lot. Okay. All right. So this equation here, I've boxed it just because, you know, we're going to use it for this problem. But, you know, if you think about it, you know, if you kind of think kind of more long term, you know, this formula only is valid for this very specific situation. Okay. Which again, you know, it does happen, you know, there's a reason we have this formula, but it's also not the only two-dimensional heat conduction situation that we have, all right? And, you know, you can imagine if you start to think of all the other types of situations that you can have, you know, having a different formula for each one kind of starts to get out of hand, right? So you start to memorize a lot of different formulas, which, you know, is just not that practical, okay? So based on this approach, you know, and based on the fact that, you know, there are certain situations that do occur more often than not, you know, we've kind of taken this idea, or engineers have kind of taken this idea and made it more general. Okay, so for this and for this formula right here, for this part that I'm circling in red, let's call this factor S. Okay. S stands for shape factor. Because if you look at that term that I've circled there, all of the variables in there are either, well, pi technically is a variable, but pi we know is just the number. But all the other variables in here are only have to do with the geometric properties of the situation that we have. Okay. So everything that has to do with the geometry, the lengths, the diameters, the depth that it's buried, all of that is there. Whereas all the thermal properties, so things like the temperature difference and things like thermal conductivity, we've kind of separated those outside. Okay? And so if we rewrite this equation and then we kind of substitute in that shape factor there, we kind of will get a general formula for heat transfer in these two-dimensional situations. Okay. So the formula we have is Q is equal to delta T K, right, multiplied by S. Okay. Where S here is our shape factor. Okay. S is a shape factor that has a specific form for certain specific geometries. Okay. So the formula that I had above there for the shape factor, that's something that's specific for a pipe that's buried underneath the ground. But there are different formulas for shape factors for different types of situations, different types of geometries. Okay. All right. Any questions on this so far? Okay, good. Okay, so here's our general equation here. And if you're curious about which other situations have a shape factor, there's actually a table for it in the book. So this will be one of the few times I actually refer to the textbook, just because the table was kind of too big to kind of write in my own notes. Okay. So table 4.1, excuse me, has a lot of different shape factors. So I have a few that are in my notes, but I think table 4.1 has anywhere between 10 or 12. It's been a while since I've looked at it, but for instance, so if you look into that table, it's going to look something like this. So there are 4 columns. So the first column is the geometry. Right. So the first column is kind of a description of the geometry in which it has the shape factor for. Second column is the picture. Okay. So the picture is there to kind of illustrate to you what that geometry looks like. Okay. It also shows you kind of where the dimensions are. So third column is going to be restrictions. Okay. So a lot of times these shape factor formulas, there's some kind of restriction in terms of a certain regime that you can use it in. Okay. And the last one is the shape factor itself. Okay. So for instance, if we look at the example that we just did, you'll find this on the shape factor table. So this is a horizontal isothermal cylinder. Buried in a semi-infinite medium. So it's a very, very long name. It's basically just a pipe that's buried underground. Okay. And so the picture for this is the following. So we have a pipe that's buried underground, where this depth right here is Z, the pipe diameter is D, and the length into the page is L. Okay.
You can't say the N word.
So there's actually two formulas here for this, depending on the rate, depending on the relative lengths of each dimension here. Okay. And so the first one is if L is much greater than D. Okay. So if the pipe is very long and the diameter is very small, then we have the following formula, which is the one that we just used. Okay? So this is 2 pi L divided by hyperbolic cosine inverse of 2z over d. Okay, so that's exactly the formula that we just had. Or okay, the other situation is if z is greater than 3d over 2. Okay, and this one also has the restriction of L much being greater than D as well. Okay, so if you're in a situation where the depth it's basically buried much deeper underground, so that the buried depth is greater than 3/2 D, then the formula for the shape factor then changes to 2 pi L divided by natural logarithm of 4z over D. Okay. By the way, so this table here is not something that I expect you guys to memorize, just because there's just way too many of them. Even for the simple cases, even for the one that we're doing in this example. If I were to give you a question on this on an exam or on the homework, my expectation is that you're either going to have the table in front of you. So if it's a homework, you'll have the textbook or you have online to look up. Or if it's given to you on an exam, I will give you this table. So this is not something you have to memorize. This is just something that that just to be aware of how to use this, because there's a lot of different shape factors that are out there. Okay. Maybe I'll give you one more example of something that's in here, and then we will do another. We'll finish the example that we had. But are there any questions on just this part of the table here? Okay. All right. So another example. Let's look at boxes actually. So let me draw this. So let's say that we want to compute the heat transfer from the edge of a box. So this one doesn't have as long of a name. Okay. So for an edge of a box, let's see. So let's say we have a box here. We'll define this length as L. And then the edge that we actually want to compute the heat transfer from is actually this one right here. Okay. So remember, that edge of the box, if you really wanted to compute the heat transfer from it, it's fully two-dimensional. And so you have heat transfer going in every direction. So, normally you'd have to solve the 2D heat equation. But with the shape factor, you can kind of do it in just one arithmetic expression. So the restrictions that we have here is D must be greater than 5L. Okay. So in other words, you can only use the shape factor formula if that edge is, at least 5 times greater than any other edge in the box. Okay. And the shape factor for this is 0.54 times D. Okay. So you'll see this sometimes too. 0.54 kind of seems like a random decimal to multiply this by. Again, this is mostly just based on empirical evidence, and so people have kind of measured in experiments. Okay, so let's do one more, just because we're going to need it for the last example. So let's do corner of a box. Okay. So the figure for this is the same. The only difference now is that we're looking at the heat transfer from a specific corner of the box right here. Okay. Okay. But once again, you know, we have dimensions of the box. We have the length in that direction we call it D. The length in this direction we'll call L. Okay. Okay. And so in this case, our restriction is that L must be much less than the D. Okay. And then the shape factor in this case is 0.15 L. Okay. Okay. So those are just a few examples of shape factors, but again, you know, if you look at table 4.1, there's a lot more in there. Okay. So when you have a 2D heat transfer situation, you know, first thing I would check is to see if table 4.1 has a shape factor for your specific situation. If it's something that occurs very commonly, it's likely going to be in table 4.1. If not, then you know you would have to solve the full heat equation. All right. Questions on this before we do one more example of this? Okay. All right. So let's do one more example. Okay. So let's say that we have a small a small cuboidal shaped furnace. Okay. And so its dimensions are, we'll say it's 50 centimeters per edge. So it's 50 centimeters by 50 centimeters by 50 centimeters. Okay. Let's say that this this furnace is made of fire clay brick, and so brick is a fairly insulating material. Okay. And so let's say the thermal conductivity of the brick is 1.04 watts per meter Kelvin. Okay. Okay. So let's say the inside of the furnace is 500 degrees C and the outside air around it is 50 degrees C. All right, so let me go ahead and draw this out. So we have a furnace here. Looks just like this. Okay. And so the dimensions is 50 centimeters, 50 centimeters, 50 centimeters. Okay. And so what we want to do, oh, let me label the temperature. So let's say that the temperature of the furnace, TF, is equal to 500 degrees C. Okay. And then the temperature of the air around it. So we're going to assume that the air is fairly still, so there's no convection. So we'll say the temperature of the air, TA, is 50 degrees C. Okay. And so what we want to do in this case is we want to compute the total heat loss from the furnace to the air. All right, and this problem also comes with a hint. Okay. So you can see we have a cube geometry here. Okay. So the total shape factor, or the total amount of heat loss that comes from this cube, is going to come from the 6 sides of the cube. right? So we're gonna have heat loss from all 6 sides. We also have heat loss from all of the edges, and so if you count up the number of edges on a cube, there's 12 of them. Okay. And there's also 8 corners. Okay. So that means we're going to need to compute shape factors for all 26 of these different geometries. Okay. Okay. And I know normally this furnace is probably sitting on the ground, but for now we're just going to imagine that it's just floating in air. So even the bottom side of the furnace is exposed to air, right? But normally, this furnace is probably sitting on some kind of surface, and then that's going to have a different, heat transfer situation. But just to keep things simple, we'll just assume that this furnace is just floating in midair. Okay. Any questions on this? Okay. So the way we're going to do this is that we're going to compute what's basically the total shape factor of this entire cube. And so the shape factor is going to basically take contributions from all 6 of the walls, all 12 of the edges, and all 8 of the corners. Okay. And so the total shape factor, we'll call it S total, is going to be equal to 6 times the shape factor of an individual wall plus 12 times the shape factor of each edge, okay, plus 8 times the shape factor of each of the corners. Okay. Okay. So we're going to compute the shape factors for each individual component here, and then just insert it in. Okay. Now I know if you look specifically back at the table, technically speaking, we don't have the formula for this edge because it doesn't fit this criteria, right? Because normally, if you want to compute the shape factor for the edge of the box, that edge has to be greater than 5 times the length. And then same thing for the corner too. We don't technically this isn't satisfied because we have a perfect cube. But we're going to assume, just because we don't have anything better, we're going to assume that we can use those shape factors for these expressions here. Okay. Okay. So making that assumption for the edges, we know this is equal to 0.54 times the length of the edge. Okay. So this is multiplied by 0.5 meters. Okay. So we know each edge is 50 centimeters. Okay. For each of the corners, this is going to be equal to 0.15 times the length of the edge, so 0.15 times, let's see here, times, 0.15 times the, times the length, so this is 0.5 meters. And then for the walls, I didn't give you the shape factor for the walls, but technically the walls are just a planar surface. And so the shape factor for the walls is actually the area, or the surface area of the wall divided by the thickness of the wall itself. Okay. Okay. And I think I actually forgot to give you the thickness of the walls. The thickness of the walls in this problem is 10 centimeters. And so for this problem, the surface area is 0.5 meters times 0.5, because it's square, divided by thickness, which is 0.1 meters. Okay. Yeah, so that was something I forgot to give you in the problem. So in the problem, the walls have a thickness of 0.1 meters. Okay. Okay. All right, so if you add all this together, and so you multiply each one by 6 and 12 and 8, then we get a total shape factor of 18.36 meters. Okay, bless you. And so if we do that, we get Q is equal to, now that we have the shape factor, we have K times delta T times S. Okay. We have the thermal conductivity of the wall that was given to us in the problem. So this was 1.04 watts per meters Kelvin. Okay. Delta T is just the difference in temperature. So this is 500 degrees C, which is the temperature of the furnace, minus 50 degrees C, okay, which is the temperature of the air. And the shape factor we just computed is 18.36 meters. So the total heat loss from this furnace to the surrounding air is 8.592 kilowatts. All right. Any questions on this here? Yeah. Yeah. So Kelvin and Celsius, they're kind of interchangeable. So you can kind of keep, yeah, they're one. You can use one or the other. Yeah, watts per meter Kelvin, or the Kelvin and degrees C is kind of interchangeable. So you can replace this with degrees Celsius. That's usually what I do for thermal conductivity, but for some reason my notes have it the other way. But degrees Celsius and Kelvin are kind of interchangeable in this situation. No, because Kelvin is just a constant offset, so there's no multiplication when you convert from degrees Celsius to Kelvin. So the units for thermal conductivity and stuff stay the same. All right, so that's shape factors, and so the idea with shape factors is to kind of just look up in the table, see if you have something in the table that matches up with your geometry, and then just use that as the shape factor. Okay. There is one last thing I want to go over with shape factors before we move on, which is you can actually combine it with thermal resistances. Okay. And after your homework actually does that as well for your next for homework 3. Okay. Okay. Actually, let me just show you the homework problem. Okay, and then I'll give you hints on how to start it. I won't actually do it for you. So in the homework, I am giving you a square channel, okay, which looks like this. And both inside and outside of the square channel, you have some kind of fluid that's moving. So you have inside, you have a fluid, and so you have TF interior and H interior, okay? And on the outside, you have a moving fluid with its own temperature. So TO, or I messed up. Should be TFO. Sorry, temperature of the fluid on the outside, and a convection coefficient HO. Okay. And what I asked you basically to do in the problem is to compute the heat transfer or heat loss from this square channel. Okay. So basically kind of exactly what we did in the previous problem, except this time you have convection. Okay. All right. So to compute this heat loss, you're going to need to combine together, this idea of shape factors as well as convection. Because what do we know about convection? So if we're given a convection coefficient and we're given the temperature, we can compute resistances for them, right? Right. So the convection resistance of the fluid on the inside is going to be 1 over HI times the surface area on the inside. And the temperature or the thermal resistance on the outside is 1 over HO multiplied by the surface area on the outside, AO. Okay. And so if we have TFI and TFO, right? Normally what we can do is we can just take the temperature difference between TFI and TFO and then divide that by the sum of all the resistances in between. Okay. That's what we would normally do. Except in this case, we don't have a situation, or we don't have a geometry that we're normally accustomed to. So we don't have it's not a cylinder, it's not a planar wall. It's it's a 2D system here. Okay. But if you look up in table 4.1, okay, table 4.1 actually has a shape factor for this situation exactly right here. Okay. So for this middle part right here, for conduction through the square channel, you can actually put a thermal resistor there as well, okay? Or that thermal resistance has to do with the thermal conductivity and the shape factor of this thing, okay? And so this resistance for conduction is going to be equal to 1 divided by the shape factor for this square channel multiplied by its thermal conductivity. Okay, and this would be something you look up in table 4.1. Okay. And if you don't have the textbook, this table was published in a lot of places. So just search up, heat transfer, shape factors, and then you'll probably get a dozen tables that look up. Okay. So you can actually take these shape factors and compute essentially a thermal resistance from them. Because if you look back at our shape at our Q formula from earlier, right? Q is equal to delta T times K times S, right? And so because we have delta T there, then the shape factor here kind of acts as kind of a pseudo resistance in those cases. Okay. So all you have to do for this problem is just complete this circuit, compute that shape factor, and then just treat it as if it were a thermal resistance. Okay. Okay, but this is a problem on homework 3, which I've almost ready. I'll probably post after homework 2. Okay. Any questions on this? Okay. All right, so that's it for shape factors. I feel like a lot of times in the class I say this is not going to take too long, but then we end up talking about it for a long time. I just yap for a long time. Yeah, questions? Lowercase k. Yeah. So that's thermal conductivity k. Okay. So for the last 20 minutes or so for class today, let's talk about transient conduction. By the way, transient conduction, this is going to be the last topic that we cover. That's going to be on the first midterm. So we're going to cover this for maybe rest of today, Thursday, and maybe next Tuesday. Then that'll be it for the first midterm. Okay. Okay. So with transient conduction, we're going to start to look at cases that are not steady state. So for the first time in this class, we're actually going to look at things which are unsteady, okay? So if you think back to the heat equation, there was always one term that we always crossed out, right? So it was the term with the time derivative. Okay. So this was our unsteady term in the heat equation. So before this, we always just assumed that this term was 0, but now we're actually going to be looking at it, okay? Okay. But, just like with 2D conduction, there's a lot of limitations in terms of, how much we can do with unsteady situations, right? Because if you look at the 1D heat equation, right, if we include the unsteady term together with the spatial derivative, we still have a partial differential equation, right? Right. I feel like I've teased partial differential equations so much in this class, but don't worry, we're not actually going to solve it. Okay. And so what are we going to do, right? And so if we include this unsteady term, we have to solve a PDE, right? But if we make kind of one key assumption here, we can avoid us having to solve this PDE. Okay. Okay. And so as is the case, with most of the time in fluid mechanics and here as well, we need to be very kind of careful with our assumptions, just to even give us a chance to solve these types of problems, okay? Okay, so what is the assumption that we're going to make here? So this assumption is quite different than everything that we've done so far. And essentially what we're going to be doing, or is we're going to assume, is that whatever object or whatever subject that we're trying to solve in our problem has a uniform temperature distribution. So it's going to be the same temperature all throughout. Okay. So the key assumption okay. So that's very different than everything that we've been assuming, because everything that we've been assuming or everything that we've been solving for up to this point, we're assuming that the temperature varies throughout the object, right? So that's kind of been key to our heat equations that we've done up to this point. Whether it be in the planar case, the radial case, spherical case, right? Everything that we've solved for so far, the temperature varies as a function of space, right? So it's a function of x or r or y sometimes or z sometimes. But for unsteady situations, we're going to kind of flip it on its head, where we're going to assume that entire temperature is, or the entire object is at the same temperature. Okay. So this assumption right here has a specific name. Okay. So this assumption here is called the lumped capacitance assumption. And while this is certainly not true a lot of the time, it can be true in certain key situations. So let's look at an example of where this can be true. Okay. So the first situation that we're going to look at is we're going to assume that we're dropping a hot piece of metal, so a piece of metal or an object that's at a very high temperature into a very cool fluid. Okay. Okay. So let's say we have a big pool of water here. Okay. So this is filled with water. And let's say that we just dropped an object. Okay. So the object can have any shape, but the point is for it to be small. Okay. Okay. And so if we look at the temperature of the object, TO, and the temperature of the fluid, okay, so we'll call the fluid temperature T infinity, okay? We're going to assume that the temperature of the object is much greater than the temperature of the fluid, okay? And so what's going to happen in this case? And so eventually what's going to happen is that because the object is at a much higher temperature than the fluid, then heat is going to escape from the object and then go into the fluid. Okay? All right. And then as heat escapes from the fluid, two things are going to happen, right? So think about, just kind of take yourself out of this class, take yourself away from the math for a second. If you drop a hot object into a big pool of water, right? What do you expect to happen? So number one thing you expect to happen is that the object is going to cool down. Okay? And if the temperature difference is pretty big, the object is going to cool down fairly rapidly. Okay? So in other words, one way we can say this is that the temperature of the object TO will drop pretty quickly. Okay. So that's a given, right? So that, and a lot of times that's what you want. Dropping a hot object, you're trying to cool it down. You drop it into a very cool fluid, it's going to cool down that object. Okay. The other thing that's going to happen, and this one may be a little bit harder to notice if unless you have a small pool of water, is that the surrounding water is going to heat up. Right? Question? Yes. Oh yeah, yeah. Mhm. Yeah. Mm-hmm. Exactly. Yeah. So the exact opposite can happen too. So you're putting like a relatively cool object into a hot, medium or hot fluid. So that's exactly what happens with pasta. That's exactly what happens if you drop an ice cube into like a drink too. And so in that case, kind of the opposite occurs. So, yeah. Mm-hmm. But generally speaking, at least for our case, point number two, we're going to assume that this is not going to happen, because we're going to assume that our fluid is so vast, right? It kind of acts as a reservoir. So any temperature difference that occurs within the fluid itself is going to be relatively negligible. Okay. Actually made my wife pasta for Valentine's Day. Made her pasta from scratch. And of course she said, it's overcooked. I'm like, I made it from scratch for you. Eggs are expensive now too. You know how much I paid for this pasta? Okay, so we're gonna assume number 2 is you know, we're not going to observe it, but we are going to observe point number 1, right? So so the temperature of the object is going to change rapidly. So if it's a hot object in a cool water, temperature is going to drop very quickly. If it's a cool object in a hot, it's going to rise rapidly. Okay. Okay. So what this means, if we look at just point number 1, right? That means the temperature of the object is going to be a function of time. Okay. And so that's exactly what we want to solve for in this situation. Okay. So under the lump capacitance assumption, notice how this temperature is not a function of x, or not a function of space. Okay. The only independent variable in that function is time. Okay. So this is quite different. So, you know, it's, you know, everything up to this point, you know, we've been solving for temperature differences in space. You know, for the first time, we're actually going to solve it in time. But because, you know, we can't solve partial differential equations, you know, time is going to be the only variable that we have. And the only way that assumption works is that if we assume that the object is at the same temperature throughout the entire object. Okay. Okay. Any questions on this so far? Okay, good. All right, so let's draw what's going to happen, right? So let's draw a control volume around the object. Okay. All right, and then let's account for all. Let's do an accounting of all the energy. Okay. Okay. So we know one source of heat transfer that's going to occur. We're going to have convection heat transfer that leaves the object, right? So as the object kind of floats down into the water, there's going to be convection heat loss coming from the object. So 1, Q convection. Okay. So this is convective heat loss to the fluid. Okay. The other thing that's happening that, you know, that we've never done before is that we can say that the internal temperature or the internal energy of the object is also changing with time, right? And so what we can say is that we have the internal energy of the object. Okay. I'm going to put a dot on top just to say that it's changing with time. So E int internal Okay, so those are our 2 major players in our energy balance here. Okay. And because of conservation of energy, these 2 things must equal out, right? So all of the heat that's leaving the object due to convection, you know, that heat is not coming from nowhere. So that heat is coming from the internal energy. Okay. And so if we balance this out, then what we can say is E internal dot plus Q convection equal to 0. Okay. So let's plug in for each of these expressions here. So we actually do have these. Okay. So Q convection, we already know an expression from this. So for Q convection here, we're going to plug in Newton's law of cooling. Okay. So Newton's law of cooling we know is H times the surface area of the object multiplied by the difference in temperature. Okay. So in this case, it's temperature of the object minus temperature of the fluid. Okay. And then for the change in internal energy, we ideally would like an expression for the internal energy in terms of the temperature of the object itself. Okay. Turns out we have this, and this does come from the heat equation. Okay. You have to kind of manipulate the terms a little bit in the heat equation in order to get this, but its origins are from the heat equation. Okay. So an expression for the time rate of change of the internal energy is rho, the object's density, times V, which is the object's volume, times C, which is the thermal capacity of the object, okay, multiplied by dt dt. Okay. So let me go ahead and label these. Rho is the object density. Okay. V here is the object's volume. Okay. And C here is specific heat capacity. Okay. And so if we put this all together, we plug those in, what we get is, so let me go ahead and separate this here. Okay. So if we plug all this in, we have rho times V times C dt dt, okay, plus H times A T minus T infinity is equal to 0. Okay. Right, so what we have here is an ordinary differential equation, okay, which we can solve this ODE for T. Okay. So this is a first order ordinary differential equation. It also has constant coefficients, and so we can solve this. We can make one small change here just to make our lives a bit easier. And so if you recall from when we talked about the Finn equation, introduce this idea of the excess temperature. So let's change to excess temperature. Okay. So make the math very slightly easier. So if we make this substitution where theta is equal to T minus T infinity, okay? And so we plug that in. We get rho times V times C d theta dt plus HA times theta is equal to 0. Okay. And so we'll pause here for now, just because I don't want to solve it just yet. We'll do that first thing on Thursday. But this equation right here is the lump capacitance equation. With only convection. Okay, so when we come back on Thursday, we'll solve for a solution to this equation here. You'll see that it's separable, so it's pretty easy. We'll find its solution, we'll talk about it, and then we'll introduce other components as well, such as prescribed heat flux and other stuff. Okay. All right, so thank you guys for coming today. Sorry, I apologize again for the technical difficulties at the start of class. Oh, question, yes. First midterm is planned for November, or not November. It's in the past. March 6th. Yeah. Believe that's a Thursday. All right, so thank you guys. Hope you have a good day, and I will see you on Thursday.
Sorry to keep asking this, but I always get confused on boundary. This is from both.
Okay.
I'm confused on like when I ask for boundary, where do I start and when?
Yeah, so for the boundary conditions, you have to kind of look at what's given to you in the problem, and then kind of go based on that. So actually, I forgot that problem. Let me actually bring it up. Which problem is this one? Problem 2? Okay. Okay, good. Okay, yeah, so for this one, so the two boundaries in this case are going to be Ri and then Ro. So essentially you can think of this, we're solving for how the temperature is going to change between these two radiuses. And so you want to look at, what's the thermal condition at this internal radius and what's the condition at this outer radius, right? So the fact that at this outer radius, we're actually given this temperature, so that's something that's actually labeled in the problem, then this is something we can plug in. So that means that's, one of the boundary conditions is going to be T, when R is equal to RO is equal to Ts. So I think you have that in your, so that was good. For the inner radius, we actually don't know the temperature. It's not given to us. But what we do know is that there is a certain amount of heat flux that's coming out. And so for this one, we actually have a prescribed heat flux. So you're going to use Fourier's law to prescribe that. Okay. Yeah, so it's all about kind of, what's kind of looking at what's in the figure and exactly what's there and sorting into one of those three categories.
Okay.
Yeah.
And
So,
then I also get confused with like the generation of heat.
Yeah.
Is there heat generation?
there is, and so you can see there's Q dot here, and so in between the inner radius and the outer radius, you have thermal production,
Okay.
and so that's going to increase the temperature as well. So the thermal production that actually comes in when you're solving the heat equation itself. So taking the integrals, that means you're going to have that extra term for the Q dot.
Okay. For sure. All right. Thank you.